Welcome back. In this video, we cover an updated R syntax, which you may want to use. Collectively, the collection of R packages is called the Tidyverse. You can install all of them with install.packages tidyverse. These packages take a renewed approach to the underlying data structures of R for faster processing. And there's an associated book that I highly recommend. I have a link here. It's a free online read, R for Data Science. There are several packages in the Tidyverse. Each has a special purpose, like data manipulation, reading data quickly, plotting, string manipulation, and even functional programming. The foundational data structure in the Tidyverse is the tibble. You can use the tibble anywhere you use a data frame in base R. But the tibble is optimized for faster performance. And the Tidyverse also has new functions to go along with the tibble. In this code block, we're using the tibble_dataframe function to convert a data frame to a tibble. The glimpse function is similar to str. Notice that we get the dimensions of the data, the types of the columns, and the first few elements. The dplyr package is used for data manipulation. Some of the functions work on columns and some on rows. First, we'll look at a few functions that work on columns. Select will select a subset of columns. So here my first argument was my tibble, and I wanted it to select just the diabetes and pregnant columns, and I pipe that to the glimpse function. The pipe is created just by typing % greater than %, which is fairly easy to type. And notice that we could have written this with this syntax here. So we take our tibble, pipe it into select, and then pipe it into glimpse. So a noticeable difference in modern R syntax is that instead of the base R way of nesting functions, they're each on a line by themselves and piped to the next function. I do think that's a little bit more readable. In these two examples, we didn't actually update tibble because we didn't write it back to the tibble. Here in the mutate, we did. We piped the tibble to the mutate function, which is going to create a new column called glucose high. That's going to be a binary factor if the glucose level was high or not. And we did write that back to the tibble, so it will update the tibble. Notice we can index the tibble just like a data frame. Here I'm just looking at the first 5 rows of columns 2 and 10 is our new column. Mutate can also be used to delete a column by just setting it to null. Notice that there's backward compatibility, so the functions that we use on data frame will also work on a tibble. There's a rename function to rename a column. Now let's look at a few of the dplyr functions that work on rows. Filter will select rows. So here I'm filtering my tibble to just include those rows where glucose is not NA and mass is not NA. We can use arrange to sort. So this gives us a view here of the data frame sorted by mass in descending order. The summarize function gives you statistical summaries. And by the way, you can spell this the British or the American way with a Z or an S. So I'm piping the tibble into summarize, and I'm asking it for the min, max, and standard deviation of mass, and specifying the headings. Here's another example. I ask it to summarize the positive and negative instances of diabetes. So we can see that 264 were diabetic and 488 were not. Group by is also very nice. I'm grouping by diabetes and summarizing the median BMI. So what we see is that people that don't have diabetes, their median BMI is 30, and for those that do, the median BMI is 34. The goal here is just to give you a reading familiarity with code using the Tidyverse. I think it's really a personal preference which style you use. Another huge part of modern R, which we'll look at in the next notebook, is Ggplot. For data exploration, I usually just use base R plots because they're one-liners with minimal typing and I can see what I want to see. However, Ggplots are great for times that you want a fancier plot. There's 7 grammatical elements in Ggplot. The first 3 of those are essential to getting something plotted. First is your data, and then is your aesthetics, the actual things that you're going to plot. The geometries are your visual elements like points and lines, and then you have optional things like facets, statistics, coordinates, and themes. Here I've loaded the Pima Indians Diabetes database again and converted it to a tibble. Let's look at our first plot. We say Ggplot. The first argument is our tibble. My aesthetics, I want to plot on the x-axis mass, on the y-axis glucose. I want points, and I also want some labels. And we see that graph over here. This next one simply adds some dot points, colors, and sizes. Also a smoothing line here. Notice with this syntax you can easily add another element like the smoothing line here, just on a line of its own. Here is a plot where I'm plotting mass and age, and I want the shape of the points to be whether or not they had diabetes. So we can see in our legend we get triangles if they're positive, circles if they're negatives, and I want the color to be the number of pregnancies. So the darker the blue, the lower the number of pregnancies. Here's an example of a facet grid. I have 2 binary variables, and so that will give me 4 windows. First, I make my binary variables. Here first I filtered out NAs in glucose and insulin, and then I used mutate to create a glucose high and an insulin high column. And those are what I'm plotting in the facet grid here. So I still have mass on the x-axis and age on the y-axis, but then we see for the 4 different levels of these 2 factors, 4 independent plots. Here's a histogram. It's fairly straightforward. Here is a box plot with the notch equals true. The color of the points is cornflower blue, and the alpha gives me a transparency of 0.5. The rug on the side here gives us where the observations are. So you can see one little line here for this observation, and most of the observations are right here. This is an example of density plots. Again, with alpha equals 0.5, it gives it that transparency. Here's a bubble chart where the size of the bubbles is the number of pregnancies. And here I'm using Grid Extra to arrange 2 plots side by side. These are just a few simple examples of what you can do with Ggplot, and this should be enough to get you started if you want to use it. Next, we'll look at some data wrangling with the Tidyverse. In the data wrangling chapter, I have some examples of dealing with time data, text data, and other data wrangling issues. I won't cover that here. Here I want to look at some things I didn't put in the chapters. This notebook is also in the GitHub, by the way. I found a data set at the UCI Machine Learning repository that looked interesting. Here's a link to it here. However, it was in Weka format. Weka is a machine learning toolkit written in Java. I've used it years ago, and so I was familiar with the file format. The data files for Weka end in .arff for attribute relation file format. My first thought was that I could write a little Python script to convert it to a CSV file, but then I thought, wait, I bet somebody already has a package for that. And sure enough, they do. It's called rweka. All I have to do is read it in and we'll convert it to a data frame. And then using TableDF, I convert it to a tibble and take a glimpse. There are 11,000 rows and 31 columns. The UCI repo link above has a Word document with descriptions of the columns. The target is result, a binary predictor of whether a URL is a phishing URL or not. First, I'm checking the distribution between phishing and not phishing. These are binary 1 and -1 encoded, and it's a fairly even distribution. Here's a different way to do a train test split. So I'm adding a row number, setting a seed for reproducibility, and then piping the tibble into a sample function to sample 75% of the indices, which in this case are the row numbers, and then doing an anti-join with that for the test set. I'm going to do logistic regression on this data set using all of the predictors, and I'm trying out a new metric here called MCC for Matthews Correlation Coefficient. Some people use it for binary classification because it will produce a high score only if all 4 categories, true positive, true negative, false negative, are classified well. The metric ranges from -1 to +1, and we got here an accuracy of 0.937 and an MCC of 0.873. So that's pretty good, but notice that when I used all the predictors, I get a really difficult to read summary here. Many extra dummy variables. Some of these predictors have 2 levels and some have 3. So they'll all have at least 1 dummy variable and some will have 2. And so that's a little bit hard to interpret. So my idea is to build a simpler model. So here I'm subsetting all of the p-values for all of the coefficients, and there's actually about 39 of them. And then I'm subsetting those that have a high p-value, greater than 0.05. And we see those here. Notice that these dummy variables will have an extra 0 or sometimes an extra -1 at the end. And I want to eliminate these columns, and these won't match. So what I'm going to do next is use stringers, string extract, and string remove functions to get rid of the extra things on the end of the column. So when I run that, I see that these are the columns I want to move, and I've eliminated those extra digits on the end. So I'm making a new tibble, which I'm calling tibble reduced, by selecting here's something I don't have in the book, using the one of with a not in front, so not one of these delete columns, and this is my reduced data set. I'm resetting my train and test sets to reflect the new number of columns and running a second logistic regression model. We see my accuracy went down a little bit from 0.937 to 0.927, so it went down 1%. And my MCC went down a little bit as well. However, the benefit is that my summary is now interpretable. So this would give me more information about what indicators are important for indicating whether a site is phishing or not. Now let's do a little digging into the data with Ggplot. I'm looking at 3 predictors here in this graph that got good p-values, but when you look at the distribution for each level, for example, DNS record has 2 levels, and for each level, I've color-coded it to be the 2 classes of phishing or not phishing, and they're fairly evenly distributed, maybe less for this predictor. And also these other 2 predictors, this one looks pretty good. The web traffic of 1 is more associated with not phishing versus phishing. And so it seems like we have a lot of fairly weak predictors. In fact, when we look back at our summary for our second model, we see that most of the coefficients center around 0, meaning that they are contributing either positive or negative way to the target, but not to a great extent. This URL of anchor seems to make a bigger magnitude of contribution to the log odds, and perhaps also this SSL final state. So I'm going to take a look at just those 2 predictors I noticed that had high magnitude coefficients. And I see that SSL final state, most of the observations here are 1, and for the other 2 states, most of the observations are -1. And also for URL of anchor, we see that for levels 0 and 1, most of our observations were class 1. Almost all for level -1 of this predictor were class -1. I want to get rid of one level in each variable for the reasons I just described, and besides, this gives me an excuse to show more data wrangling. I'm creating a third tibble, TB3, from the TB reduced tibble using mutate with replace. This will update the column in place. I'm changing levels of -1 to 0, doing a similar thing with the URL of anchor column, making levels 0 and 1, 1, and level 1, 0. Resetting train and test again and making a third model, I see that my accuracy is down to 0.90 and my MCC is lower as well. But let's look at the summary. Our summary, of course, is highly interpretable, and this is a decent model of the data because notice our null deviance went from 11,000 down to 4,000. Of the three models, it's not the best model. Clearly, model 1 is the best. But we've learned something useful about the data, and that is that most of the predictive power of phishing or not is in these two predictors. Why would we ever want a less accurate model? Well, we wouldn't, but sometimes exploring different models gives you insight into the data, and that's what machine learning is all about. By the way, I just used logistic regression here for simplicity. Other more complex algorithms might get better results. But in this notebook, we've gotten more practice with data wrangling and machine learning. And we also learned a new metric that you might want to use in your own projects when you have a binary target. This wraps up our linear models. The next set of algorithms we look at group observations by similarity metrics, a totally different approach to machine learning.